Good afternoon, class. We are looking at Chapter 2, Limits, Section 2.1, Limits of Sequences. In this chapter, Chapter 2, Limits, we are going to cover 2.1, Limits of Sequences, 2.2, Limits of Functions at infinity, 2.3, Limits of Functions at finite numbers, and finally 2.4, Limits, Algebraic Methods. So let's recap what we did in section 1.6. So recall, 1.6 was about sequences and difference equations. A sequence is a list of numbers written in a specific order, a sub 1, a sub 2, all the way to a sub n. First, second, nth terms of the sequence. A sub n is the general term and n is the set of positive numbers. 1, 2, 3, 4 to infinity. Recursive sequence, also known as difference equation, is in the form of a sub n plus 1 is f of a sub n. The next term depends on knowing the previous one or previous ones. For example, everybody remembers Fibonacci sequence. F1 is 1, F2 is 1, F sub n in general is F sub n minus 1 plus F sub n minus 2 when n is larger than or equal to 3. Meaning if you are looking for a term, find the previous two and add them up. So the first one starts with 1. There is nothing before that, so the second one is 1 also. Add these two, you get 2. Add these two, you get 3. Add these two, you get 5. So on and so forth. That's a Fibonacci sequence, which happens in nature a lot. Arithmetic sequence, a sub 1 plus d, all the way to a sub 1 plus n minus 1 times d. D is a common difference. So a sub n plus 1 is a sub n plus d in the form of recursive format. Explicitly, a sub n is a sub 1 plus n minus 1 times d. A geometric sequence is in the form of a sub 1, a sub 1 times r, a sub 1 times r squared, all the way to a sub 1 r to the power of n minus 1, where r is a constant known as the ratio. So a sub n plus 1 is r times a sub n. Recursively, explicitly, a sub n equals a sub 1 r to the power of n minus 1. So again, reminding everybody, so we are going to go to 2.1 limits of sequence. Here's the summary and reminding everybody a sequence is an ordered list of numbers or function f whose domain is the set of natural numbers or positive integers 1, 2, 3 to infinity. Limit refers to the long-term behavior of a sequence, i.e. what happens to a sub n of a sequence in the long run. The limit of a sub n as n approaches infinity equals L. We say that a sub n converges to L. Limit of a sub n as n approaches infinity is infinity, or limit of a sub n as n approaches infinity is negative infinity, or DNE does not exist. We say the sequence diverges. To find limits, simply plug in the value and observe. We're going to discuss this with more details. I'm going to go over some theorems, and here's the summary. This theorem, the limit of r to the power of n as n approaches infinity depends on the value of r, the base. If the base is between 0 and 1, or better yet, between -1 and 1, it's 0. If it's 1, 1 to the power of n is 1. And if it's larger than 1, is infinity. Okay? To understand this, if I go with a couple of examples, for example, if you have 1 over 5 to the power of 1 is 1 over 5, 1 over 5 squared is 1 over 25, which is smaller than 1 over 5. And if I cube that, it's 1 over 125, which is even smaller. And therefore, it's referring to the fact that it ends up being 0 as we continue and we make the exponent larger as it approaches infinity. On the other hand, 5 to the power of 1 is 5. 5 squared is larger, 25. 5 cubed is even larger, 125. And this indicates that when n gets larger and larger, if r is larger than 1, it tends infinity. So that's one of the theorems that has a lot of usage. The limit of 1 over n to the power of p as n approaches infinity is 0 for p larger than 0. And that's really the key, because if p is negative, this comes up. Remember, if we look at 1 over a to the power of minus m is the same as a to the power of m. Okay? Or a to the power of minus n is 1 over a to the power of n. So if you have a negative exponential, you can move and take it down or up to make the exponent positive, and that's why p must be positive. Geometric sequence, when we add them up, is called geometric series. S sub n is the summation of a r to the power of n minus 1 as n goes from 1 to infinity. It gives us a plus a times r plus a r squared. And here's the sum, a times 1 minus r to the power of n over 1 minus r. If you recall, this was done in algebra, in college algebra and pre-calculus. I will look at the proof of that later on. And what happens if r is between negative 1 and 1 according to this, then we know this goes to 0, right? And therefore, the limit is a over 1 minus r. Now, in the case of a geometric sequence, b sub n plus 1 equals r b sub n, that's the recursive format, or b sub n equals b sub 0 r to the power of n explicit format. And in many texts, they use a instead of b sub 0. So these two equations are identical, everybody. One uses a, and one uses b sub 0. It's the same thing, okay? I wanted you to be exposed to that. However, if we add a constant to this formula, it becomes a little bit more complicated. And as you recall, this is like giving medication to patients, where R is the remaining portion, is the percentage that remains in the body, and the constant will be added at a specific time step. Then it gives rise to this formula, or this formula, by the way, again, b sub 0 or a, b sub 0 or a, and this is, I have the proof for you at the end if you want to look at the proof. Let's look at some warm-up example. What happens to a sub n of the following sequence? We want to calculate the first few terms. This one, I think, is pretty obvious. If I put 1, I get 1 over 1, which is 1. If I get 2, I get 1 over 2, or 0.5. So this one is 1 over 1. This one is 1 over 2. And if I continue with that, I get 1 over 3, 1 over 4, 1 over 5, 1 over 10, or 0.1. And it's getting smaller, and I get to 0. So by putting a few numbers, we should recognize this limit is 0, and therefore it's convergent. We can also recall this theorem that was mentioned. The limit of 1 over n to the power of a p equals 0 for p larger than 0. And I hope you realize p is 1 for this example. If we were to graph it, it will look like this. Because it's discrete, we have just the dots. But you may recall from algebra, 1 over x, y, or f of x equals 1 over x. The graph looks like that with a vertical asymptote being the y-axis and a horizontal asymptote being the x-axis. So this is in essence this portion, of course, discretely. For this one, in order to see what happens, let's plug in 1. If I plug in 1, negative 1 to the power of 1 is negative 1. If I put 2, negative 1 squared is positive 1. In other words, when n is odd, if I put 3, I get negative 1. If I put 4, I get positive 1. When n is odd, I get negative 1. And when it's even, when n is even, I get positive 1. Which means it oscillates or it alternates between the two numbers. Therefore, the limit does not exist. And it diverges. So the limit of b sub n as n approaches infinity, that doesn't exist, everybody. So you could write, if you like, the limit of negative 1 to the power of n as n approaches infinity does not exist, and therefore it alternates. I can't it diverges, therefore it diverges. I can't emphasize understanding the concept as to why this is the case, okay? Why this is the case. And if you were to graph it, it looks like this, which shows the numbers jump from one value to the next. Therefore, they oscillate. Therefore, they oscillate, okay? There is no limit. There is no limit. All right, let's move on, everybody. A sequence can be shown in the form of braces. A sub n has a limit L, and we write as follows. Let A sub 1, A sub 2, and A sub n be a sequence, and L be a real number. We write the limit of A sub n as n approaches infinity is L. So we are elaborating on that summary that we had. If we can make A sub n arbitrarily close to L for all n sufficiently large, we also say A sub n converges to L. That's the concept of convergence, when we can pinpoint a number. For example, if we have two sequences, one of them is A sub n, one of them is B sub n, both of them are convergent, and C is some number. When we say the limit of A sub n plus B sub n as n approaches infinity equals limit of A sub n as n approaches infinity plus limit of B sub n as n approaches infinity, it means the limit of the sum is the sum of the limits. The limit of the difference is the difference of limits. If you have a constant, you can take it out. The limit of the product is the product of the limits. The limit of the ratio is the ratio of the limits. As always, the denominator can't be 0. If you have a power, then you can take that exponent outside. So the limit of h sub n to the power of p as n approaches infinity is the same as the limit of h sub n as n approaches infinity to the power of p. P and h sub n are both positive. The limit of a constant, regardless of the value of a constant, is always constant when n approaches infinity. For example, if it's 5, the answer is 5. It's 10, the answer is 10, and so on and so forth. Again, I'm reminding you of this theorem. The limit of 1 over n to the power of p as n approaches infinity is 0 for p larger than 0. We write the limit of a sub n as n approaches infinity is infinity if we can make a sub n arbitrarily large for all n sufficiently large. Finally, we write the limit of a sub n as n approaches infinity is negative infinity if we can make a sub n arbitrarily negative for all sufficiently large. And these last two, the sequences diverge in the last two cases. So divergent versus convergent. Convergent means you can pick up a specific value, one value, and that's the limit. All right, here's a warm-up example, and I'm reminding you of this theorem. Remember, you're supposed to know the theorem so you'll be able to handle the questions. And so with that being the case, how do we find the limit as n approaches infinity of 2 to the power of n minus 1 over 6 to the power of n? First, we make up two fractions, which means we cut this into the fraction 2 over n over 6 over n and minus 1 over 6 to the power of n, and we keep the limit, of course. Now, this one, as you know, it's 1 over 3 to the power of n, right? Think about it. 2 over 6 is 1 over 3. Now, this one, if I put, remember, 1 or 1 to the power of n makes no difference. If I change this to 1 to the power of n, I can write this as 1/6 to the power of. So I write them in this fashion so I can move on by using the limit laws and say the limit of the difference is the difference of the limits. And now we know this one is 0 because 1/3 is in this category or in this category. Between, you can say it's between 0 and 1 or negative 1 and 1. The same is 1/6, and the final answer is 0 minus 0, which makes it 0. We want to find the following limits. And as I mentioned, all you have to do is just plug in and observe. So let's plug in. In this case, we're going to plug in infinity. 2 to the power of infinity falls into this category when the exponent is larger than 1, okay, and it becomes infinity. They didn't ask, but if they did, it diverges. In this case, we plug in. Now, what is 2 to the power of negative infinity? Using exponential rules, a to the power minus m is 1 over a to the power of m. This is the same as 1 over 2 to the power of infinity. Of course, the power of infinity is infinity. 1 divided by that becomes 0, because if you are dealing with a fraction, regardless of what the numerator is, if the denominator is huge, the fraction gets closer and closer to 0. So this is 0. 5 plus 0 makes it 5. And again, it converges. It wasn't asked, but you can clearly see that. For part C, we plug in, and 1 over infinity, we should know it's 0, and therefore the answer is 1. And it converges, and you're done. Another method is if you look at this one and say, you know what, P or this one, Celsius to the power of 1, P equals 1, and therefore the answer is 0, okay? So you could either way see the answer is 0. When you add it to 1, becomes 1, and therefore the sequence converges. All right, we want to find this limit, and I'm going to go over that. You've seen similar things in algebra when you wanted to find asymptotes, okay, graphing rational functions and asymptotes. I will go over that in a moment, but even that, the proof is the method that we're going to do here. If you are finding the limit when n is approaching infinity, and you're dealing with a fractional format, doesn't have to be even rational format. If it's a rational function, you divide by highest degree term in the denominator. If it's a fractional format, by highest value in the denominator. So I'm going to divide by n squared, which means I'm going to divide every term by n squared, or I multiply by 1 over n squared. Please understand, division by n squared or multiplication by 1 over n squared means the same thing. I should actually write this as just multiplication by 1 over n squared. That's what I mean, okay? So it's important to understand that, okay? And so with that being the case, we do them one by one. And what do we get? This one gives us 2, this one gives us 5, this one 3 over n, this one minus 1 over n, this one minus 1 over n squared, this one 8 over n. And I hope you see that all of these terms, this one and this one and this one and this one go to 0 except 2 and 5. The final answer is 2 over 5. Okay, so very straightforward, everybody. What happens to this case? N is approaching infinity just as before. We divide by highest degree term in the denominator. Term by term. Everything in the numerator, everything in the denominator. This is what you get. This gives you 3 over n. This gives you minus 1 over n squared. This gives you 7. This gives you minus 3 over n. So I hope you see that this one, and this one, they go to 0. The denominator is 7. Now, why is this 0? Pay attention to the fact that you are dealing with 0 over 7. 0 over some number other than 0 gives you 0. If it's 0 over 0, which we will discuss it later on, is called indeterminate form. We don't want to mix them up. Okay. What about here? Same thing. N is approaching infinity. We divide by highest degree term in the denominator, but this time this is n. So again, multiplication or division. Multiplication by the reciprocal, so dividing by n, or multiplying by 1 over n. So each one is done. One by one, we get the following. N, the limit as n approaches infinity of n over 2 minus 1 over n. So plug in, you get infinity, 2 minus 0. And infinity over 2 is also infinity. What I want to explain is this. Infinity over any number a positive number. Let me actually clean up the whole mess. Okay, and what I want to write this is, of course, n squared if you multiply. Infinity if you divide by any positive number. Doesn't matter. Divide by 10, 5, 5,000, 1 billion is infinity. If it's negative infinity. Square root of infinity, cube root of infinity, infinity squared, infinity times, I don't know, 5 or 10 or 2. They are all infinity. Okay? They are all infinity. And I hope all of them are infinity, everybody. So when we say infinity divided by 2, that is equal to infinity. All right. We are asked to calculate the first 8 terms and find the limits. So the first term is 2. Don't have to do anything. And a sub n plus 1 is 1 minus 1/3 a sub n. This is the general term. So the next one is a sub 2. All you have to do, say, okay, if this is 2, what do I do? If this one is 2, if n plus 1 is 2, then n is 1. And so replace the a sub 1 with 2. One minus 2/3 is 1/3, and I'm done. The next one, if n plus 1 is 3, n must be 2. So a sub 3 is 1 minus 1/3 a sub 2. Replace the a sub 2 with 1/3. The product is 1/9. 1 minus 1/9 is 8/9. And clearly, if we could calculate a couple of them, we can calculate all of them. That's not a problem. So I want to write this table. The first one, we know it to be 2. The second one is 1/3. The third one is 8/9. And we can write the rest of them and go through the process. However, it takes a little bit of a time. I want to show you a different method also that you can do using a calculator to speed up the process. So just, again, I'm going to emphasize, if you can show work for 2 of them, you can show work for all of them. Here's the methodology for a calculator. A sub n, whatever the values you store, this is storing in x. And then the formula for a sub n plus 1, because the limit exists, the limit for this one and a sub n ultimately becomes the same. Both of them, you can replace it with some value, x, 1/3, and so forth. Because you put this in x, we're going to do the same thing here, and we are going to write according to this, okay? We're going to write 1 minus 1/3 x, store it in x, and press enter key repeatedly. You get them. Notice the first one is a 2, as expected, because we stored the 2 in it. And then when we put it into this formula, we get a 0.3 bar. As you know, that's 1/3. The next one is 0.8 bar, and so on and so forth. So if you write all of them in this table, okay, this is from a calculator. I'll quickly show you how to use that calculator. This is what we get. And according to the table, the 8th one seems to be getting closer and closer to this number. I think you should be able to detect that according to this, the sequence converges to 0.75. If you don't see that, you can do a couple more, or maybe 5 more. and you'll see the answer. Now, what I want to show you, and you have a question similar to that in my open math, I want to show you analytically or algebraically the proof that the answer is 0.75. So if the limit exists, then at some point, no matter how far we go, things don't change. So for example, this may keep on changing, but if you go to the 20th term, then it's the same as the 21st one. That, and remember, n is approaching infinity. So the limit of a sub n plus 1 as n approaches infinity is the limit of a sub n as n approaches infinity, if the limit exists. Otherwise, that's not the case. They keep on changing otherwise. So if that is the case, and we know this formula, a sub n plus 1 is 1 minus 1/3 a sub n. If I take the limit of the left side, is the same as the limit of the right side. And since this one is L, I'm going to replace this with L. 1 gives me 1, and this one also gives me L. L, in this case, is representing the limit. This is a simple algebraic equation. I am going to move this and make it positive 1/3 L on the left side, and they add up to 4/3 L. And if I multiply this one by the reciprocal 3/4, then I find L to be 3/4, and everybody knows 3/4 is the same as 0.75. What I want to quickly show you, if we want to use this calculator in the manner that I mentioned, okay, we put a sub 1, which happened to be 2, into x. We store it into x. Enter. And then 1 minus 1/3 x, store it in x. 1 minus the parentheses 1 divided by 3, close parentheses, x stored in x. Enter it, and look at our number 0.33 here. If you enter, you get the next one. If you enter, you get the next one, and the next one, and the next one. So I hope you see that it's really not that big of a deal if you continue. The purpose of that is to speed up your process and make life easy, okay, class? Not that you replace it. As far as this concept that I wanted to mention regarding limits of rational functions are concerned, I want to remind you that what you learn in algebra when y or f of x was given as a sub n, x to the power of n, all the way to a sub 0 over b sub m, x to the power of n, all the way to b sub 0. The degree of the numerator, where the numerator is n, or the denominator is n. If n is less than m, then we have HA, also known as horizontal asymptote. Y equals 0. That's why the limit becomes 0 in some case. And I'll go back and I'll show you in our work. if n equals m, then the horizontal asymptote has the equation y equals a sub n over b sub n. And if n is m plus 1, then y or f of x can be written as mx plus b plus some remainder over the denominator. Then we have slant or oblique asymptote y equals mxb. Of course, in the last case, the limit goes to infinity. And so just to see what we are discussing here, I want to show you when we looked at this example, okay? And let me put that in slide mode. It makes it easier to see if I put all of them next to each other. Okay, notice this one, the degree of the numerator was 2, the denominator was the same thing. So the answer was just the leading coefficients, y equals 2/5, or the limit is 2/5. In this case, the degree of the numerator was 1. In this case, the degree was 2, which was larger. So the limit was 0, or y equals 0 was the asymptote. In this case, the limit for the degree of the numerator is 2, the bottom is 1. And since this is larger, there is no horizontal asymptote. There's a oblique asymptote that you can find through long division. But no matter what, this goes to infinity. I just wanted to remind you of this concept that you have learned in algebra.